Welcome back to our series on introductory statistics. I'm Mark Ledbetter. This is lecture video 40. We are in section 9.2, part 5. Previously, in this chapter, we have discussed the situation where we did not know mu, and we wanted to do a hypothesis test about the population mean mu when we did know sigma. Now, this is not a very realistic case, but it is a case that does occasionally occur. So since then, we've been looking in section 9.2 at the case that's more realistic, that occurs more often in real life. That is where we are performing a hypothesis test about the population mean mu when sigma is not known. So we're using the sample standard deviation as an estimate. I hope you will enjoy this pre-recorded video. Let's look at our second example again. Bill Althor is a zoologist who studies Anna's hummingbirds, the Calyptae Anna. Suppose that in a remote part of the Grand Canyon, a random sample of 6, so this tells me n is equal to 6, of these birds were caught, weighed, and released. The sample mean, x bar, is 3.75 grams. Let x be a random variable representing the weights of Anna's hummingbirds in this part of the Grand Canyon. We assume that x has a normal distribution, which is the only way we can do this problem since n is equal to 6. There are ways to do it if you have a different distribution, but we're not going to cover that. It's a little more advanced. So it has a normal distribution, and here I changed that instead of saying that sigma was 0.7, I'm saying the sample has a standard deviation s is equal to 0.7. So we don't know the mean, we don't know the standard deviation of the population, but the mean of the whole population is approximately 4.55 grams. Do the data indicate that the mean weight of these birds is less than 4.55 grams? Use the same alpha, 0.01. Requirements: normal distribution for data. So yes, we meet the requirements. Hypothesis statement: H naught mu is equal to 4.55 grams versus the claim, which is, the claim is that the mean weight of these birds in this part of the Grand Canyon is less than 4.55. I see the less than here, so that means mu less than 4.55. So the claim tells you what sign to put in H1 in the alternative. Now my test statistic, because I don't know sigma, I have to use t observed equals square root of n x bar minus mu over s. And so square root of 6 x bar is 3.75. And then I go to my null hypothesis and I see that it says that mu is 4.55, so I substitute that in for mu. And then divide by s, which is 0.7. I carefully enter this into my calculator using parentheses. And I get, let's see, did I get the same thing I got last time? Oh, I used the wrong sample at 6. That's why I didn't get the same answer. So I get negative 2.799941 something. And for a t-table, I'm going to move that to 3 decimal places, round it to 3. So I go to the 4th, that's not a 5 or above, so I'm going to leave it at 2.799, negative. Okay. So now I need to look at my critical region. P-value is less than alpha. So remember that this can be called rejection criteria, the critical region, or the rejection region. It all means the same thing, just different words for it. Okay? We know that alpha is 0.01. We need to find our p-value. So here we draw the t distribution and we have a negative 2.799, and we want this area below it is our p-value. Let's go to our, before we go to our t-table, we need to look at the degrees of freedom, which is n minus 1, which is 6 minus 1, which is 5. So now I'm going to this row with 5 as my degrees of freedom. And I'm going to try to find, since I don't have negative numbers up here, I'm going to use just the value 2.799, and that will give me the same answer. Remember, this left-tailed area here on the picture for negative t is the same as the right-tailed area for positive t. So I have a negative 2.799, and in this row I need to see where that would fall, and that's going to fall right in here between 2.575 and 3.365. And so that is going to be between 0.025 and 0.01. Okay. So now my p-value, I'm going to make it red so we can see it after I erase this. It's going to be between 0.025. Actually, I'm going to write it in reverse because it's going to be the small number, 0.010 to 0.025. That's what we saw. So we don't know what it is exactly, but we know that it's not exactly, let's see, what value gave me 0.01? That was 3.365. So this one gives me the cutoff, 0.01. And we're smaller than that, so that means that we're going to have a p-value that's greater than 0.01. So we have a value that's greater than between, we can say, somewhere between 0.01 and 0.025. So now this is no longer a true statement because our p-value is greater than 0.01. It's not less than 0.01. And so now it's not a true statement. So we do not reject H naught. Now notice that we've got the same value for our test statistic. Right? Everything's set up exactly the same. We get the same value for the test statistic. What's different is our p-value. Well, let's go with purple. Our p-value here is somewhere, it's much higher than it was before. Let's see what our p-value was last time. So we come down to this problem, and our p-value, when we use z, was 0.0026. And remember when we said, well, what if we use the two-tailed test and we had to double the p-value? It was still less than 0.01. But because we only have 5 degrees of freedom, okay, we only have a sample size of 6, our value for t is very different than our value, the probability for our t statistic is very different than our probability for the z test statistic. All right, so instead of getting these values, or when we did one-sided, we've got a p-value of 0.0026, and it was less than 0.01. But using degrees of freedom equals 5, we got a p-value that was greater than 0.01, which is much greater than 0.0026. Okay? And so our decision is do not reject H naught, or we fail to reject H naught. there does not exist sufficient evidence to support the claim that the mean weight of these birds in this part, mean weight of these birds in this part of the Grand Canyon are, less than, or have a mean weight, we said the mean weight, are less than 4.55 grams at a 99% confidence level. Remember, C equals 1 minus alpha, and we had 1 minus 0.01, which is 0.99, which is 99% confidence level using a simple random sample of size 6. Okay? So, now, I want to point out that the sample size has a huge effect when we're looking at the t distribution. So let's take a look here at 0.01, this column right here. Now if we take a look at this and we think, okay, we need to be 0.01 is the maximum, so we need to be smaller, because you see 0.005 and 0.0005, they're over here. So we need a value that's on this side to the right. Okay. So as we start with degrees of freedom 3, we need to be, it looks like, bigger than 4.541. And then this number is getting smaller. So we would need to have, in order to be, we had negative 2.799. So we would need a number that is, we would need degrees of freedom of 10, so we'd have to have n equals 11 in order for that same test statistic, 2.799, to be significant. Okay? So for that value of negative 2.799, you'd need at least n equals 11 in order for that value to be significant at a 0.01 significance level, okay, for alpha equals 0.01. So for the t test statistic, n is very important. The smaller n is, the harder it is to reject the null hypothesis. The larger n is, the closer it gets to the value of z for 0.01, which would be 2.326. All right? So as n goes towards infinity, the t statistic approaches the standard normal, or z statistic. And we talked about that in the last chapter, in chapter 8, when we talked about the confidence intervals, and we introduced the t-table. But I just wanted to reinforce that. So these two examples, I hope that these help you. Now, as you can see, that if we changed this to a two-sided test, and we set H0 or H0 mu equals, what was it, 4.55 versus H1 mu is not equal to 4.55, then our p-value equals 2 times what we had before, which is between 0.01 and 0.025, yes, 0.025. So it would be between 0.02 and 0.05 And so if we fail a one-tailed test, if we fail to reject a one-tailed test, we'll certainly fail to reject a two-tailed test. Okay? So that's the relationship between the two. It's more difficult to reject the null hypothesis for a two-tailed test than it is for a one-tailed test. All right? So I hope this has been helpful doing your homework. In the next video, we'll do a few more examples to help you get this concept solidified. Well, that's the end of this video. Please remember to scan your lecture notes before midnight of the date listed on the course calendar. If you have questions, please come to virtual office hours. I am very happy to help you, as always. If you can't do that, then you're welcome to email me. But when you email me, I need two things from you. The first is a picture of the problem so that I can help you through email. I may not have the problem available to me. If you don't send me the problem, then you're going to have to wait until I get back to my computer and get that problem pulled up. So please send me a picture of the problem. The second thing you need to send me is a picture of your work so far. This helps me understand how you're approaching the problem and may help me or will help me help you faster and better. So I hope you will stay safe and take care of yourself. Until next time, we'll see you then.